Imagine waking up tomorrow morning and reaching for your coffee, only to watch it leap from the table, assemble itself perfectly into an unbroken mug, and land gently in the cabinet above the counter. Imagine watching the sun rise in the west, arc across the sky, and set in the east. Imagine remembering yesterday with perfect clarity, but having absolutely no idea what today will bring, because today, in this reversed world, is something that has not happened yet, or rather, something that has already unhappened. Imagine being unable to speak a word until after the person across from you has already responded to it. Imagine a world where wounds close before the knife arrives, where forests grow younger every year, where the dead rise from their graves and walk backwards into the lives they once lived, getting younger, getting smaller, until one day they are simply not there anymore, unborn, unwound, erased. This is not science fiction. Or rather, it is not only science fiction. The question of what would happen if time began flowing backwards is one of the most profound, most terrifying, and most legitimately scientific questions that any human mind has ever attempted to answer. It sits at the intersection of physics, philosophy, neuroscience, thermodynamics, cosmology, and something so deep and primal in the human experience that it almost defies categorization. It is a question that the greatest minds in the history of human thought have wrestled with, sometimes at the cost of their sanity, sometimes at the cost of their careers, and always at the cost of their comfortable assumptions about what the universe is and what it means to exist inside it. And here is the thing that should make you stop cold, right now, before we go any further. The fundamental laws of physics, the equations that govern how particles move, how forces act, how energy transfers. Almost all of them work perfectly well in both directions. You can run the mathematics of classical mechanics forward and backward and get equally valid results. You can run quantum mechanics forward and backward. You can take the equations of electromagnetism and reverse the direction of time, and they still hold. The deep mathematical machinery of the universe, as best as human science has been able to decode it, does not care which way time flows. It does not prefer forward. It does not demand a past and a future. It is, in the coldest and most dispassionate sense, completely symmetrical with respect to time. So why does time flow forward at all? Why does it feel so profoundly, viscerally, irreversibly one-directional? Why can you remember breakfast but not dinner? Why does the egg shatter on the floor and never reassemble? Why do you grow old instead of young? Why does everything, every single thing you have ever experienced, move in one direction, from past to future, from cause to effect, from birth to death? If the laws of physics do not demand this, then what does? And more terrifyingly, what would happen if that direction suddenly, catastrophically, cosmically reversed? These are the questions we are going to answer today. And I promise you, by the time we are finished, you will never look at time the same way again. You will look at your own memory differently. You will look at the universe differently. You will look at the arrow of your own life, that single, relentless, forward-moving trajectory. And you will feel, perhaps for the first time, what an astonishing, unlikely, and deeply fragile gift it is. Let us begin at the very beginning. Not the beginning of time, necessarily, though we will get there. Let us begin with something more immediate. Let us begin with what time actually is. This is already a question that most people assume they can answer but cannot. Ask someone what time is, and they will say something like, "It's how we measure the passing of moments." Ask a physicist what time is, and they will pause in a way that tells you something important is happening. The physicist knows, in a way most people do not, that time is one of the deepest mysteries in all of science. Saint Augustine, writing in the 4th century, captured it perfectly when he said, "What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know." That is not a rhetorical dodge. That is a genuine and enduring confession of ignorance that has not been fully remedied in the 16 centuries since he wrote it. The ancient Greeks had two different words for time. Chronos referred to sequential, quantitative time, the ticking of seconds, the measurement of duration. Kairos referred to qualitative time, the right moment, the opportune instant, the sense that not all moments are equal. Both of these concepts capture something real. Both of them are incomplete. Neither of them quite gets at what physicists today mean when they talk about time as a dimension of space-time, interwoven with the three dimensions of space in a four-dimensional fabric that curves and warps in response to mass and energy. Isaac Newton thought of time as absolute. In his mechanical universe, time was like a great river flowing at a constant rate, equally for everyone, everywhere. It was the fixed stage on which the drama of physics played out. Newton did not ask what time was, fundamentally. He assumed it was there, and he built his extraordinary mathematical machinery around that assumption. For 2.5 centuries, his picture of time was so successful, so predictably powerful, so elegant in its machinery, that almost no one felt the need to question it. Then came Albert Einstein, and everything changed. In 1905, Einstein published his special theory of relativity. And in that theory, time was no longer absolute. Time was relative. It flowed at different rates depending on your velocity. The faster you moved, the slower your clock ticked relative to someone standing still. This was not a theoretical abstraction. It has been measured, tested, confirmed to extraordinary precision. GPS satellites, orbiting the Earth at high speed, experience time at a slightly different rate than clocks on the ground. If you did not correct for this effect, GPS navigation would drift by miles within days. We correct for it routinely, because it is real. Because Einstein was right. 10 years later, Einstein expanded this into his general theory of relativity. In general relativity, time is not only relative to velocity, it is relative to gravity. Clocks run slower in stronger gravitational fields. Time passes more slowly at the bottom of a mountain than at the top. This too has been measured. This too is real. There is a genuine, measurable, experimentally confirmed sense in which the universe's gravitational landscape warps the flow of time the way a heavy ball warps a rubber sheet, distorting the geometry of space-time itself. And this is where things get philosophically vertiginous, because in Einstein's universe, time is not a river flowing through space. Time is a dimension, a direction, embedded in a four-dimensional space-time manifold. The physicist Brian Greene describes it this way. In relativity, space and time are so thoroughly intertwined that different observers moving at different velocities will disagree not just about when events happen, but about whether events are simultaneous at all. Your now and my now are not the same. They are not even objectively comparable without specifying a reference frame. The universe does not have a universal, cosmic present moment. It has a tangle of overlapping, observer-dependent nows, each of them equally valid, none of them privileged. Now ask yourself this question, and really sit with it for a moment. If time is a dimension just like space, if the past and the future are, in some sense, just different locations in a four-dimensional landscape, then why do we move through time in only one direction? You can move east or west, north or south, up or down. Why can you not move backward through time the way you can walk back the way you came? Physicists have a name for this puzzle. They call it the arrow of time, and it is one of the greatest unsolved problems in all of science. The phrase arrow of time was coined by the British astrophysicist Arthur Eddington in 1927. Eddington was one of the most eminent scientists of his era, the man who led the 1919 expedition that confirmed Einstein's predictions about gravity bending light during a solar eclipse, an experiment that made Einstein world famous. And Eddington, thinking deeply about what distinguished the past from the future, noticed something extraordinary. He noticed that there was really only one physical law that gave time a direction, only one law that distinguished the past from the future. That law was the second law of thermodynamics. The second law of thermodynamics is one of the most beautiful and devastating things in all of science. It says that the total entropy of a closed system always increases over time, or at best remains constant. Entropy, loosely speaking, is a measure of disorder, of randomness, of the number of possible microscopic arrangements that correspond to a given macroscopic state. When you break an egg, entropy increases. The organized structure of the egg becomes disordered fragments. When you burn wood, entropy increases. The complex molecular structure of the wood becomes simpler molecules. Heat, light. When a hot cup of coffee cools in a cool room, entropy increases. The thermal energy disperses from a concentrated, ordered state into a diffuse, disordered one. And here is the key point. You have never seen it happen in reverse. You have never watched a broken egg spontaneously reassemble. You have never watched heat flow from a cold room into a hot cup of coffee, making the coffee hotter while the room cools further. You have never watched smoke flow back down into a chimney and condense into firewood. These things do not happen. The second law of thermodynamics forbids them, not by making them physically impossible in principle, but by making them vanishingly, astronomically, incomprehensibly unlikely. The physicist Richard Feynman, one of the most brilliant and colorful figures in 20th century science, loved to explain this with a thought experiment. He would say, imagine a movie of a ball bouncing on a floor. You can run the film forward or backward, and both look perfectly physical. The ball goes up and comes down, or it goes up and comes down in reverse. Either way, it obeys Newton's laws. Now imagine a movie of a glass falling off a table and shattering into 100 pieces on the floor. Run it forward, it looks completely normal. Run it backward, the shards fly up from the floor, assemble perfectly into a glass, and leap onto the table. This looks immediately, viscerally, unmistakably wrong. Why? Not because any law of physics is being violated at the microscopic level. Each individual atom in that glass is obeying Newton's laws perfectly, whether the film runs forward or backward. But the collective behavior of those atoms, the spontaneous self-organization of 100 glass shards into a perfect cup, is so astronomically improbable that it effectively never happens. The physicist Ludwig Boltzmann was the first to understand this deeply, and it essentially drove him to suicide. Not metaphorically, not as an exaggeration, literally. Boltzmann, working in the late 19th century, derived a mathematical connection between entropy and the probability of different microscopic arrangements of atoms. His famous formula, S equals K log W, where S is entropy, K is Boltzmann's constant, and W is the number of microscopic arrangements corresponding to a given macroscopic state, is considered one of the most important equations in all of physics. It is engraved on his tombstone in Vienna. But Boltzmann spent decades defending his statistical interpretation of thermodynamics against fierce opposition. Many leading physicists of his day did not believe in atoms, let alone in the probabilistic interpretation of entropy. His work was attacked, his sanity questioned, his contributions belittled. In 1906, while on vacation in Italy, Ludwig Boltzmann hanged himself. He was 62 years old. Within a few years of his death, experiments had confirmed the existence of atoms beyond any reasonable doubt, and Boltzmann's statistical mechanics became one of the cornerstones of modern physics. He never knew he had won. But even Boltzmann's victory left a deep puzzle intact. His statistical mechanics explained why entropy increases over time. But it could not by itself explain why entropy was so low to begin with. And that is the real mystery at the heart of the arrow of time. Think of it this way. The reason the future looks different from the past, the reason eggs break but do not reassemble, the reason we grow old but do not grow young, the reason we remember yesterday but not tomorrow, is that the universe started out in an extraordinarily low entropy state. In the moments just after the Big Bang, the universe was in a state of almost incomprehensible order and organization. Not because it was neatly arranged in any obvious visual sense, but because, thermodynamically, the distribution of energy and matter was extraordinarily smooth, extraordinarily constrained, leaving enormous room for entropy to grow. And for the past 13.8 billion years, entropy has been growing. The universe has been, in the thermodynamic sense, becoming more disordered. Stars are burning, galaxies are colliding, black holes are consuming, Heat is dispersing. And we, on the surface of a small rocky planet, are embedded in this great cosmic unwinding. We age because entropy grows. We die because entropy grows. We remember the past and not the future because the past was lower in entropy than the present, which creates a systematic asymmetry in the traces and records and memories that exist in our brains and in the physical world around us. So now we have arrived at the central question. What would it actually mean for time to flow backwards? And what would happen if it did? There are multiple ways to interpret this question, and each one leads to a different and fascinating set of consequences. The first interpretation is the most physically rigorous. What would it mean if the entropy gradient reversed? If instead of increasing, entropy began to decrease over time? The second interpretation is more experiential. What would it be like if you, as a conscious being, began to experience time in reverse? If your memories were of the future rather than the past, if you were aging backward, if cause and effect were inverted? The third interpretation is cosmological. What if the entire universe, at some point in its future evolution, reversed its direction of time? And the fourth interpretation is perhaps the most philosophically radical. What if time's direction is not a physical fact but a psychological construction? And what happens when that construction breaks down? Let us take each of these in turn. Let us go deep into each one, because each one reveals something extraordinary about what time really is, and what the universe really is, and what it means to be a conscious creature embedded in the flow of time. Start with the entropy reversal. Start with the physics. And start with a question you can ask yourself right now, at home, wherever you are listening to this. Ask yourself, if the universe started in a low entropy state and entropy has been increasing ever since, what does that imply about the future? If entropy has been growing for 13.8 billion years, how much further can it grow? And more importantly, is there any physical reason why, at some point, it could not reverse? The answer, shockingly, is no. There is no fundamental physical law that forbids entropy from decreasing. The second law of thermodynamics, as Boltzmann showed, is a statistical law, not an absolute one. In a sufficiently large system, over a sufficiently long time, random fluctuations will occasionally produce local decreases in entropy. In a small system, a tiny box of gas, for example, you might wait only seconds or minutes for a fluctuation that briefly lowers entropy. In a larger system, you might wait billions of years. In the universe as a whole, you might wait a time so long that it makes the age of the universe seem like a flicker. But statistically, in an infinite universe with infinite time, entropy reversal is not only possible but inevitable. This is what physicists call a Boltzmann fluctuation, and it has one of the most mind-bending implications in all of cosmology. The physicist Roger Penrose has pointed out that the vast, overwhelming majority of Boltzmann fluctuations that produce an observer with memories, with a brain that contains records of a past, would produce that observer directly, without any need for a long physical history leading up to that moment. It is vastly more probable, statistically, for a single brain to fluctuate into existence complete with false memories of a lifetime of experience than for an entire universe to fluctuate out of a low-entropy initial state and evolve for billions of years into the complexity we observe. This hypothetical entity, a brain that fluctuates into existence out of chaos, complete with memories and perceptions, existing for a brief moment before dissolving back into disorder, is called a Boltzmann brain. And the fact that standard cosmology seems to predict that Boltzmann brains should vastly outnumber real observers like you and me is considered one of the deepest and most troubling problems in modern theoretical physics. Now, here is where we need to slow down and really grasp something. Because the Boltzmann brain problem is not just a weird statistical curiosity. It goes to the heart of why the arrow of time exists, and what it would mean for that arrow to reverse. The physicist Sean Carroll, one of the foremost living experts on the arrow of time and the author of the book From Eternity to Here, argues that the real mystery of the arrow of time is not why entropy increases. That follows straightforwardly from probability. The real mystery is why entropy was so extraordinarily low at the beginning. Why did the universe start in such an improbable, tightly constrained, thermodynamically special state? And what preceded that beginning? Carroll's own preferred answer involves a model in which our universe is not the only one, and not even the typical one. He argues for a picture of a multiverse in which universes are continually sprouting from a parent to sitter space, a universe dominated by a cosmological constant, a repulsive dark energy that drives exponential expansion. In Carroll's picture, the parent universe has no particular arrow of time. It does not have a preferred direction of past or future. Baby universes nucleate from it, and some of these baby universes happen to have very low entropy at their nucleation point. For those universes, and we live in one, entropy will increase away from that low entropy moment in both directions. Time will have an arrow that points away from the low entropy beginning. Read that again. In both directions. This is extraordinary. In Carroll's model, if you could look forward from the Big Bang and also backward from the Big Bang, you would see entropy increasing in both temporal directions away from that initial moment. An observer living in the universe on the other side of the Big Bang, in the time before our beginning, would experience time as flowing in what we would call the negative direction. They would age, they would remember their past, they would experience cause before effect, but their experience of time's arrow would be opposite to ours. They would be, from our perspective, aging backward and living in a world where time flows in reverse. This is not science fiction. Sean Carroll published these ideas in peer-reviewed physics journals, and while they remain speculative and contested, they are taken seriously by the professional physics community. They represent one of the most genuine and rigorous attempts to answer the question of what lies at the origin of the arrow of time. But let us bring this down from the cosmic scale and make it immediate and personal. Let us talk about what time reversal would actually look like and feel like in the world you inhabit right now. Think about your morning. You woke up. You were groggy, confused for a moment. Then memory assembled itself and you knew who and where you were. You stumbled to the bathroom. You brushed your teeth. You made coffee. You checked your phone. Each of these actions had a sequence, a direction, a before and after. And crucially, you knew which way that sequence ran. You did not have to think about whether the coffee went into the cup before you drank it or after. You did not have to wonder whether the toothpaste went onto the brush before or after you brushed your teeth. You knew. You knew because you were the cause of these events, and because your memory recorded the sequence in real time as you lived through it. Now imagine that the arrow of time reversed. Not gradually, not predictably, just suddenly, irrevocably, completely. What would you experience? The first and most immediate thing to understand is that this is genuinely one of the hardest questions in all of philosophy of mind and cognitive science, because your experience of time is not a passive recording of external events. It is an active construction of your brain. Your brain is not a camera. It does not simply capture the world as it is. It actively interprets, predicts, constructs, and narrates your experience of reality, including your experience of time. The neuroscientist David Eagleman, who has done some of the most fascinating experimental work on the subjective experience of time, has shown that the brain constantly edits and reorders its perception of temporal sequences. There are well-documented phenomena in which the brain perceives the effect before the cause, at least in terms of conscious experience, because different types of sensory information are processed at different speeds and then retrospectively edited into a coherent narrative. When you catch a ball, for example, the motor response initiates before conscious awareness of the intention to move. When you watch a movie, the rapid sequence of still images is assembled into a seamless flow by your brain's temporal processing machinery, not by the camera. So your experience of time flowing forward is, in part, a story your brain tells you. It is not direct, unmediated access to an objective temporal reality. It is a construction. And this raises the deeply unsettling question. If time began flowing backwards, would you know? Would your brain simply adjust its construction and continue to tell you a coherent story, but now a story that ran in the opposite direction? Or would the reversal produce a catastrophic breakdown in cognitive coherence, a kind of temporal psychosis in which cause and effect could no longer be distinguished, in which memory became prophecy and anticipation became recollection? This is not merely a thought experiment. There are real neurological conditions that give us glimpses of what temporal disorientation looks like. Patients with certain forms of amnesia experience profound disruptions of their temporal sense. The famous patient known as HM, who had his hippocampus surgically removed to treat severe epilepsy, lost the ability to form new long-term memories. For the rest of his life, after the surgery, he lived in an eternal present. He could not remember events that had happened minutes ago. He was unable to place himself in time. His experience of the temporal narrative of his own life was shattered. He could still experience the immediate present, still engage in conversations, still perform many tasks, but the thread that connects moments into a coherent temporal flow was severed. He could not move forward through time in any meaningful subjective sense, because moving forward through time requires the ability to remember where you have been. Now imagine this condition, but inverted. Imagine being able to remember the future with perfect clarity, but having no memory whatsoever of the past. This is, in a sense, what time reversal would mean for a conscious being. You would know, with absolute certainty, what would happen in the next hour, the next day, the next year, because all of that would be in your past, in your reverse temporal experience. But you would have no memory of yesterday, of last year, of your childhood, because all of that would be in your future, ahead of you on the reverse timeline, not yet reached in your reversed experience. Can you feel how disorienting this is? Can you sit with it for a moment? Because it gets stranger. In a world where time runs backward, from the perspective of a reversed observer, what we call the future would be fixed and known, because it is already in their past. What we call the past would be open and unknowable, because it is their future, not yet reached, containing genuine uncertainty. This is the mirror image of our temporal experience. We remember the past, but cannot know the future. A time-reversed being would know the future, but could not remember the past. And here is where the philosophy gets genuinely vertiginous. We think of the past as fixed and the future as open. This feels intuitively obvious. The past has already happened. It is done. It is determined. The future is uncertain, undecided, full of branching possibilities. But is this actually a fact about reality, or is it a fact about our position in time? A perspective that would look completely different to a time-reversed observer. The philosopher of physics David Albert, in his remarkable book Time and Chance, argues that the apparent openness of the future is directly connected to the thermodynamic arrow of time. We experience the future as open because we are in a low-entropy universe where the future has higher entropy than the past, and higher entropy means more possible microscopic arrangements, which translates into more uncertainty about what will happen. In a time-reversed universe, where entropy was decreasing, the past would be higher entropy than the present, and thus more uncertain, more branching, more open, while the future would be lower entropy, more constrained, more determined. The concepts of fixed and open, of determined and uncertain, would completely reverse. This means that free will, or at least the intuitive sense of making choices that genuinely affect an open future, would be experienced very differently in a time-reversed world. A time-reversed being would feel as though they were making choices about their past, not their future. They would feel as though their actions now were determining what had already happened before they were born. This is so alien to our intuitive sense of causality and agency that it almost defies imaginative grasp. But it is logically coherent. It is what time reversal actually implies. Now let us go even further. Let us leave the individual and look at the world around us. What would time reversal actually look like in the physical world? What would you see if you were somehow able to watch a time-reversed universe from outside? Let us start small and work our way up. Start with a stone dropped into a pond. In our forward time universe, the stone hits the water and produces a series of concentric ripples that expand outward in all directions. In a time-reversed universe, those ripples would contract inward from all directions, perfectly converging on a single point, and then eject a stone upward from the water. This seems miraculous. This seems to require an impossible coincidence. How would all those ripples know to converge perfectly? But in a time-reversed universe, this would not require a coincidence at all. It would simply be what happens when a stone is caught from the water. The ripples are not converging by coincidence. They are the time-reversed image of the outgoing ripples. The convergence is as natural and inevitable in the reversed universe as the expansion is in ours. This example illustrates something profound about why time-reversed processes look so improbable to us. They look improbable because we are pattern matching them against our forward time intuitions. A convergent ripple looks like a coincidence because we know how hard it would be to engineer one from scratch in our world. But in a time-reversed world, it is not engineered. It is automatic. It is the natural direction of wave behavior in that temporal context. Now scale this up. In a time-reversed universe, light would not radiate outward from hot objects. It would converge inward on cool objects, making them hotter. Heat would flow from cold regions to hot regions. Stars would not shine outward. They would absorb light from the cosmos and become cooler, denser, until eventually they would somehow, and this is where the picture becomes genuinely bizarre, reverse the fusion reactions in their cores. Helium would split back into hydrogen. The star would contract and cool further. Eventually, the time-reversed universe would see stars becoming more organized, more structured, over time. The opposite of what stars do in our universe, where they burn through their fuel and eventually die. In our universe, stars form from clouds of gas, collapse under gravity, ignite fusion, burn for millions or billions of years, and then die, either collapsing into neutron stars or black holes, or exploding in supernovae that scatter heavy elements across space. The time-reversed version of this process begins with the death of a star, which then somehow gives rise to the scattering of heavy elements, which then concentrates into a star, which then unburns, which then eventually uncollapses into a gas cloud. And all of this would look, to a time-reversed observer, as completely natural and expected as stellar evolution looks to us. Here is a thought experiment for you to do right now. Picture in your mind the most chaotic, disordered scene you can imagine. A demolition site, perhaps, where a building has just been brought down with explosives. Concrete dust billowing in every direction. Twisted steel beams. Fragments of glass. The wild, unpredictable sprawl of collapsed architecture. Now imagine watching that scene in reverse. The concrete dust pulls together. The steel beams straighten and reconnect. The glass fragments fly up and reassemble into windows. The building rises, floors clicking back into place, walls reconstructing themselves, until the structure stands again, whole and unharmed. This looks like magic. This looks like the most extraordinary thing you have ever seen. But to a time-reversed observer, watching you use explosives to bring down a building is equally astonishing. They see you taking this perfectly organized, intact structure and deliberately introducing energy in a way that produces chaos. They see the increase in entropy, the spreading disorder, the violence of what we casually call demolition. And to them, it looks like the miracle. The question of whose perspective is right is not merely rhetorical. In the fundamental equations of physics, both perspectives are equally valid. There is no preferred direction. The forward time observer and the time-reversed observer are both obeying the same physical laws. The only asymmetry is statistical, and the statistics depend entirely on where you start, on the initial conditions of your universe, on whether your universe begins in a low-entropy state or ends in one. Now let us go up to the biological scale, because this is where time reversal becomes truly strange and deeply moving, in a way that cold physics alone cannot convey. Consider a tree. In our world, a tree begins as a seed, a tiny, compact, extraordinarily organized structure containing all the information needed to build the full organism. The seed germinates, sends roots down and a shoot up, grows over years or decades into a full tree, produces its own seeds, ages, and eventually dies. The aging process involves a decrease in the complexity and organization of the tree's cellular machinery. entropy increasing at the biological level. The tree's heartwood develops, its bark thickens and furrows, its branches grow heavy with years, and finally it falls and decomposes, returning its constituent molecules to the soil. In a time-reversed universe, all of this would run in the exact opposite direction. A tree would begin as a dead trunk on the forest floor. Over time, it would become less decomposed, not more. Its cellular structure would become more complex and organized. It would stand upright. It would grow leaves, or rather, it would undrop leaves, drawing them back from the ground and attaching them to its branches. It would grow younger, its bark smoothing, its heartwood becoming sapwood, its trunk narrowing, until finally it would shrink into a sapling, into a seedling, and then into a seed. And that seed would be absorbed into the ground, disappearing back into the soil from which it came. To a time-reversed observer, this is what a tree's life looks like. And to them, what we call growth is death, and what we call death is birth. But here is the point that cuts deepest. Here is the thing that keeps physicists and philosophers awake at night. In a time-reversed world, where does the information for that seed come from? In our world, the seed contains the information, the DNA, the molecular blueprint, and the tree unfolds from that blueprint. In the time-reversed world, the tree is collapsing into a seed. The information in the seed is not the starting point, it is the ending point. The seed is the final compressed state, not the initial generative one. So what directs the process? What ensures that the reverse decomposition produces, precisely and exactly, a seed of the right species, with the right genetic information? The answer is that in a time-reversed universe, there would be nothing mysterious about this, just as there is nothing mysterious to us about how a seed grows into a tree. The laws of physics would guarantee it, just as they guarantee the forward process in our universe. The information would not need to come from anywhere new, because all the relevant information would already be present in the physical state of the system. It would just be encoding the history of the tree's future, rather than its past. But, and this is crucial, this only works if the time-reversed universe is a complete mirror image of our universe, with every particle, every quantum state, every field configuration exactly reversed. If you took our universe and ran the film backward, you would get a universe that is exactly time-reversed, in which every process runs in the opposite direction. But that reversed universe is not a universe in which a random reversal has occurred in the middle of time. It is a specific, deterministic reversal of a specific history. The information for every event in the reversed universe comes from the time-reversed image of our future. This is why a genuine reversal of time's arrow, a spontaneous change in which entropy suddenly begins decreasing rather than increasing, is so different from simply running a film backward. A film run backward shows you a time-reversed universe in a coherent, lawful way, but only because you started with a coherent, forward-running universe and mechanically reversed every element of it. A genuine entropy reversal, happening in an otherwise forward-running universe, would not produce this beautiful coherent time reversal. It would produce something far stranger and less organized. A universe in which entropy was decreasing in some places while increasing in others, in which different parts of the universe had different arrows of time, and in which the coherence and consistency that we associate with physical law began to fracture. The physicist Price, in his book Time's Arrow and Archimedes' Point, explores the implications of this with great rigor and imagination. Price argues that the apparent asymmetry of time, the fact that we find advanced waves, not retarded ones, the fact that effects follow causes rather than precede them, the fact that we remember the past rather than the future, is not built into the fundamental laws of physics at all. It is built into the boundary conditions of our universe. The extraordinarily low entropy of the Big Bang. Change those boundary conditions, Price argues, and you change the arrow of time completely. In a universe with a low entropy future boundary, time's arrow would point backward relative to ours. And in a universe with low entropy boundaries at both ends, both beginning and end, time would be, the word Price uses is neutral. Neither past nor future would be privileged. Causality, as we understand it, would not apply in any simple sense. Now here is a question for you to ask yourself, and really let it land. In our universe, the initial low entropy of the Big Bang is what gives us our arrow of time. But why was the Big Bang low entropy? Was that an accident? Was it a law? Was it a selection effect? Meaning, perhaps, that only low-entropy Big Bangs produce observers who can ask the question? Or was it something else entirely? Roger Penrose has argued, with great mathematical sophistication, that the initial low entropy of the Big Bang requires an extraordinary fine-tuning that cannot be explained by chance or by the known laws of physics. He has calculated that the probability of our universe's initial state, given the laws of thermodynamics and the number of possible states the universe could have been in at the moment of the Big Bang, is 1 divided by 10 raised to the power of 10 raised to the power of 123. This is a number so small that it cannot be written out in any conventional notation. It is a number smaller than the probability of any event ever described in the history of science. Penrose argues that this extraordinary improbability demands an explanation, and he has proposed a specific cosmological model, conformal cyclic cosmology, in which the explanation comes from a cyclical structure of universes, each beginning where the previous one ended, with the boundary conditions of the Big Bang being determined by the far future of the previous cosmic cycle. In conformal cyclic cosmology, what we call the Big Bang was actually the endpoint of a previous universe. The universe before ours went through its own long evolution, ended in a state of maximal expansion and complete dissipation, a state of heat death dominated by an increasingly sparse distribution of photons, and then, through a mathematical transformation involving the conformal geometry of spacetime, that remote future state became the initial state of our Big Bang. The low entropy of our beginning was not an accident. It was the inevitable consequence of the thermodynamic end state of the universe that came before us. This is mind-bending stuff, and it is directly relevant to the question of time reversal, because in conformal cyclic cosmology, the very concept of a beginning and an end is relative to which cycle you are in. To an observer in the previous universe, our Big Bang would be their far future, their ultimate end. To us, their entire history is our past. The arrow of time in the previous universe and the arrow of time in our universe might be aligned or opposed, and the precise nature of that relationship is one of the open questions that Penrose and his collaborators are actively working to understand. But let us step back from cosmology for a moment and return to something more immediate. Let us return to the question of what time reversal would feel like from the inside. Because we have been talking about entropy and boundary conditions and Boltzmann fluctuations, and these are real and important, but they can feel abstract. Let us make this personal. Let us make it human. Imagine that you have a friend. Let us call her Eleanor. Eleanor is a perfectly normal person in every way. She goes to work, she has dinner with her family, she walks her dog, she worries about the future and occasionally wishes she could undo things from the past. Eleanor is, in short, you, or someone very much like you. Now imagine that tomorrow morning, Eleanor wakes up and finds that time is running backward for her. Not for the universe. Not for anyone else. Just for her. What would Eleanor experience? The first thing to understand is that Eleanor's brain, her memories, her thought processes, her cognitive architecture, are all physical systems embedded in the physical world. If time reversed for Eleanor but not for the universe around her, then Eleanor's brain would be doing something physically impossible by normal standards. It would be processing information in reverse while the rest of the universe processed it forward. This would create an immediate and catastrophic conflict. In our forward time universe, Eleanor's neurons fire in patterns that encode memories and drive actions. The causal chain runs from past to future. She sees something, her neurons process it, she forms a memory, she makes a decision, she acts. If time reversed for Eleanor's brain while the world continued forward, then Eleanor's brain would be doing the reverse. It would be forming a memory before the event that caused it, making a decision before being aware of the reason for it, acting before the stimulus that provoked the action had occurred. From Eleanor's reverse perspective, this would feel entirely normal. She would experience the stimulus after the response, which in her reverse time is the normal causal order. From everyone else's perspective, Eleanor would seem to be responding to things before they happened. She would seem to be prescient, uncanny, preternaturally aware of events before they occurred. This is actually a scientifically interesting possibility, and not just a thought experiment. Physicists have explored, in complete theoretical seriousness, the possibility of particles that travel backward in time, and these particles, called tachyons, are the subject of genuine research. More directly, the physicist John Wheeler proposed a thought experiment known as the delayed choice experiment, in which, and this is verified by actual quantum mechanical experiments, the behavior of a photon in the past can apparently be influenced by a measurement made in the future. The physicist Anton Zeilinger and his collaborators have actually performed versions of this experiment, and the results confirm what quantum mechanics predicts. In some sense that is deeply difficult to interpret, the future measurement affects the past behavior of the photon. This is not, to be clear, evidence for time travel or backward causation in any simple sense. But it is evidence that the relationship between cause and effect in the quantum world is stranger and more subtle than our everyday intuitions suggest. The physicist John Bell proved, in what is now known as Bell's theorem, that quantum mechanics cannot be reconciled with our ordinary intuitions about causality and locality, that there is something genuinely non-local and temporally strange happening at the quantum level, confirmed experimentally beyond any serious scientific doubt. The 2022 Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger specifically for their experimental confirmation of quantum non-locality, the deep, foundational quantum weirdness that Bell's theorem reveals. Now, let us return to Eleanor. Eleanor, in her backward time existence, would face an extraordinary practical problem: communication. In our world, you speak words in order, from beginning to end of a sentence, and the listener hears them in the same order. This works because both speaker and listener are moving forward in time together. If Eleanor were moving backward in time while you were moving forward, then from your perspective, Eleanor would be speaking the words of each sentence in reverse order. She would say the last word first and the first word last. You would hear a stream of reversed sounds. You would think she was making no sense whatsoever. From Eleanor's reverse perspective, you would be the one speaking in reverse. More than that, communication requires a shared temporal frame. Conversation depends on the listener hearing what the speaker says and then responding. But if Eleanor is reversed and you are forward, then the sequence of conversational turns would be scrambled. What Eleanor experiences as her response to something you say, you would experience as happening before you said the thing that prompted it. The entire protocol of human communication, the back and forth, the sequence of statement and response, would break down completely. This thought experiment reveals something important. Causation is not a private experience. It is a shared structure. The reason we can communicate at all, the reason language and society and cooperation are possible, is that all of us are embedded in the same causal order, moving through time in the same direction. A being moving backward through time in a forward time world would not merely be inconvenienced. They would be profoundly, tragically isolated. Every interaction with the forward time world would be scrambled and incoherent. They would be unable to participate in the shared causal order that makes human life human. There is actually a beautiful piece of fiction that explores this idea with unusual depth and care. The novel Time's Arrow by Martin Amis follows a Nazi doctor backward through time, from his death to his birth, and the narrative is told from the perspective of a consciousness within the protagonist who experiences time forward while the body experiences it in reverse. The result is a sustained, extraordinary meditation on guilt, responsibility, and the nature of causality. What makes the novel work is not its fantastical premise, but its relentless exploration of what it would actually mean to experience life in reverse, to misunderstand the direction of cause and effect, to experience cruelty as kindness and kindness as cruelty, to see the Holocaust as a creative act rather than a destructive one, simply because one is seeing it from the wrong end. Martin Amis was exploring a moral and literary theme, but his intuitions align with a scientific point. Time reversal would not merely be an inconvenience. It would be a radical restructuring of what it means to act, to intend, to cause, to create, to destroy. The concepts of guilt and responsibility, which depend essentially on the idea that past actions cause future consequences, would be entirely transformed in a time-reversed world. Now let us push into even stranger territory. Let us talk about the quantum mechanics of time reversal, because this is where the physics gets genuinely exotic and where some of the most interesting recent scientific discoveries live. In quantum mechanics, the fundamental equation that governs the evolution of a quantum system, the Schrödinger equation, is time-symmetric. If you replace t with negative t in the Schrödinger equation, you get an equally valid equation. This means that quantum mechanics, at the fundamental level, does not distinguish between past and future. A quantum system evolving forward in time and a quantum system evolving backward in time are both equally allowed by the Schrödinger equation. But there is a subtlety here. Quantum mechanics has two different kinds of processes. The first is the smooth, deterministic, time-symmetric evolution described by the Schrödinger equation. The wave function of a quantum system evolves in a completely predictable, reversible way as long as you do not make a measurement. The second is the measurement process itself, the so-called collapse of the wave function, in which the quantum system is forced into a definite state by an interaction with a measuring apparatus. This measurement process is not time-symmetric. It is random, irreversible, and deeply asymmetric between past and future. The wave function collapses to a definite state in the future. It does not uncollapse from a definite state in the past. This asymmetry in the measurement process is one of the most hotly debated issues in the foundations of quantum mechanics. Different interpretations of quantum mechanics handle it very differently. In the Copenhagen interpretation, the standard textbook version, the collapse of the wave function is taken as a fundamental, irreversible process. In the many worlds interpretation, championed by Hugh Everett and more recently by David Deutsch, there is no collapse at all. The wave function simply keeps evolving smoothly, with every quantum measurement producing a branching of the universe into multiple branches, each corresponding to a different measurement outcome. In this picture, the Schrödinger equation is always perfectly time-symmetric, and what appears to be irreversibility is actually just the proliferation of branches, which looks irreversible from within any single branch. The many worlds interpretation is deeply controversial, but it is taken seriously by a substantial minority of physicists, including some of the most eminent. And it has a striking implication for time reversal. In a many worlds universe, time reversal would correspond to the anti-branching of the multiverse, to branches of the wave function recombining rather than splitting. This process, called quantum decoherence in reverse, or quantum coherence, is something that physicists are beginning to explore experimentally in the context of quantum computing. A quantum computer, at its core, is a device that maintains and exploits quantum coherence, keeping quantum superpositions alive long enough to compute with them. And some quantum computing algorithms work by, in a sense, reversing the flow of quantum information, by undoing operations, by exploiting the time-symmetric character of quantum mechanics in ways that classical computers cannot. This is not purely theoretical. In 2019, researchers at the Moscow Institute of Physics and Technology, along with collaborators at the United States and Switzerland, performed an experiment using a quantum computer to apparently reverse the direction of time for a quantum system. They prepared a quantum bit, a qubit, in a particular state, allowed it to evolve forward in time under a quantum algorithm that mimicked the natural spreading of a quantum wave function, and then applied a special operation that reversed the spreading, effectively running the qubit's time evolution backward and restoring it to its original state. The experiment was widely reported in the popular press as physicists reverse time, which significantly overstated the case, but the underlying physics was genuine and interesting. They had demonstrated that the time-symmetric character of quantum mechanics can be exploited using a sufficiently intelligent algorithm to reverse the evolution of a quantum system. The crucial caveat is that they did not reverse time. They reversed the quantum state of a specific tiny system using a sophisticated algorithm that required knowledge of the future state of the system. They used information to engineer a time reversal, rather than reversing time itself. But the experiment illustrated, in a concrete and vivid way, that quantum mechanics does not forbid time reversal at the level of individual systems. It is the statistical behavior of large ensembles of systems, the domain of thermodynamics, that makes reversal effectively impossible at the macroscopic scale. Now let us talk about something that brings time reversal even closer to everyday experience. Let us talk about memory. Because memory is, in a very deep sense, the reason we experience time as having a direction. Your sense of the past, your autobiographical memory, your sense of being a continuous self with a history, is the direct result of the thermodynamic arrow of time. In a low-entropy universe where entropy increases over time, the past leaves traces. When something happens, an event, an interaction, a collision, it leaves marks. A footprint in the sand, a scar on the skin, a notation in a ledger, a pattern of connections between neurons. These traces accumulate over time, and it is from these accumulated traces that your brain constructs a narrative of the past. Your memories are not direct experiences of past moments. They are reconstructions from traces, from physical marks left by past events in the present state of your nervous system. This is a crucial insight. Memory is a thermodynamic phenomenon. It is the detection of the trace left by a past event in the current state of a physical system. And this means that memory inherently points backward in time. It tells you about the direction from which entropy was lower. In a world where entropy was decreasing rather than increasing, traces would not accumulate in the same way. Instead of the past leaving marks on the present, the future would leave marks on the present. Or rather, the present would carry information about a future that is becoming more organized. You would, in a very real sense, remember the future. The philosopher of physics Jen Ismail, in her book The Situated Self, explores how the temporal structure of our consciousness, including memory, anticipation, and the sense of now, is deeply conditioned by our thermodynamic situation. She argues that the asymmetry between memory and anticipation is not merely a fact about the cognitive architecture of the brain, but a fact about the physical structure of the universe that our brains are embedded in. Change the thermodynamic structure, and you change the cognitive structure. A being with a reversed thermodynamic arrow would have a reversed psychological arrow as well. And this raises a question that is both scientifically interesting and personally haunting. The question is, could there be, right now, regions of the universe where the arrow of time is running in the opposite direction from ours? Could there be, somewhere in the vast cosmic darkness beyond what we can observe, pockets of decreasing entropy, regions where time flows backward relative to our own? And could there be, in those regions, conscious beings who experience time in the opposite direction, who remember what we would call the future and anticipate what we would call the past? The physicist Lee Smolin, one of the founders of loop quantum gravity and a genuinely maverick thinker in theoretical physics, has explored the possibility that the arrow of time is not a global feature of the universe but a local one. In some of his more speculative writings, Smolin has suggested that different regions of the universe could have different local arrows of time, set by local thermodynamic conditions. In such a universe, the concept of time's direction would be as locally variable as, say, the direction of gravity, pointing differently in different places, always determined by local physical conditions rather than by any global preference. This idea is far outside the mainstream, and Smolin himself acknowledges its speculative character. But it illustrates the range of possibilities that become available once you take seriously the idea that the arrow of time is not a fundamental feature of the laws of physics, but an emergent feature of boundary conditions and thermodynamic circumstance. Now, let us talk about something that might be the most viscerally disturbing aspect of time reversal: what it would mean for causality. Because causality, the principle that causes precede their effects, that actions have consequences, that the future is shaped by the past, is not just a physical principle. It is the foundation of ethics, of law, of everything that we mean by responsibility, accountability, and the very concept of making a choice. In our universe, causality flows forward. You do something now, and the consequences unfold in the future. If you are cruel to someone, they suffer afterward. If you build something, it stands afterward. If you make a promise, you are bound by it in the future. This temporal ordering of cause and effect is so fundamental to human moral and legal thinking that we almost never notice it. It is like water to a fish, so pervasive that it is invisible. In a time-reversed universe, causality would still exist. There would still be a consistent relation between earlier and later states in the reversed temporal order. But from our forward time perspective, this would look like effects preceding causes. It would look like the consequences coming before the actions that supposedly produced them. It would look, from our point of view, like prophecy, like reverse fate, like a universe in which the future determines the past. And here is something that will stop you cold. There is a real and serious interpretation of quantum mechanics in which exactly this is the case. Not as a metaphor, not as a thought experiment, but as a literal description of how quantum systems work. This interpretation is called the two-state vector formalism, or the transactional interpretation of quantum mechanics, developed by the physicist John Cramer in the 1980s. In Cramer's picture, quantum events are mediated by two waves, a retarded wave that moves forward in time, and an advanced wave that moves backward in time. A quantum interaction is a kind of handshake between these two temporal waves, a negotiation between the future and the past. The probabilities that quantum mechanics predicts are, in this picture, the result of contributions from both the past history and the future state of the system. Cramer's transactional interpretation is not widely accepted, but it is a coherent and self-consistent interpretation of quantum mechanics that makes all the same predictions as the standard Copenhagen interpretation. And it takes seriously the idea that the future is not merely an open possibility waiting to be actualized by the present, but an active participant in determining what happens now. The physicist Yakir Aharonov and his collaborators have developed a related formalism called the two-time state or the ABL rule, which demonstrates that the probabilities of quantum measurements can be made more precise, conditioned more tightly, if you have information about both the past preparation of the system and the future measurement outcome. In other words, the future constrains the present in quantum mechanics in a mathematically rigorous and experimentally verifiable way. Aharonov won the Wolf Prize in Physics in 1998, and his work on the foundations of quantum mechanics is widely respected. His two-time formalism is a serious and profound attempt to take time symmetry in quantum mechanics seriously at the level of interpretation, not just of equations. So what does all of this add up to? What is the cumulative picture that emerges from physics, from thermodynamics, from quantum mechanics, from the philosophy of time, from the neuroscience of temporal consciousness? What can we actually say about what would happen if time began flowing backwards? The first thing to say is that the question does not have a single, clean answer, because it depends on exactly what you mean by time beginning to flow backwards. If you mean a local fluctuation, a region of the universe where entropy begins to decrease, then the result would be a region where the local arrow of time is inverted, where complex structures spontaneously form from simpler ones, where heat flows from cold to hot, where biological organisms reverse their aging. If you mean a global reversal of the universe's temporal direction, a cosmic change in the thermodynamic history of everything, then the result would be something far more radical. A universe running in the opposite direction from ours, with its own arrow of time, its own causality, its own form of consciousness and memory, but all of it pointing the other way. And if you mean the personal experience of a single conscious being whose subjective temporal experience is reversed while the universe continues forward, then the result would be something tragically and beautifully alien. A being who knows the future, cannot remember the past, experiences effects before causes, and is utterly unable to participate in the shared temporal world of everyone around them. The second thing to say is that the reversibility of time's arrow is not merely a theoretical curiosity. It has deep, immediate, and urgent implications for some of the most important open questions in physics today. The mystery of the arrow of time is directly connected to the mystery of the Big Bang, to the question of why the universe began in such an extraordinary state of low entropy. It is connected to the mystery of quantum measurement, to the question of what happens when we observe a quantum system and it appears to collapse into a definite state. It is connected to the mystery of the cosmological constant, to the question of why the universe is currently accelerating in its expansion, driven by a mysterious dark energy that makes up about 70% of the total energy content of the cosmos. And it is connected to the mystery of black holes, to the question of what happens to information when matter falls into a black hole and apparently disappears from our universe. That last connection is perhaps the most exciting and most recent. The question of what happens to information in black holes is one of the hottest topics in theoretical physics right now, and it is directly connected to time and its arrow. The physicist Stephen Hawking showed in 1974 that black holes are not perfectly black. They emit a form of thermal radiation, now known as Hawking radiation, caused by quantum effects near the event horizon. This radiation carries energy away from the black hole, causing it to slowly evaporate over an astronomically long time. And the key question is, does the information about everything that fell into the black hole come out in the Hawking radiation, or is it permanently lost? For decades, Hawking himself argued that the information was lost, that black holes destroyed information, violating a fundamental principle of quantum mechanics known as unitarity. The physicist John Preskill bet Hawking a baseball encyclopedia on this question. In 2004, Hawking conceded the bet, acknowledging that the AD/CFT correspondence, a mathematical duality between certain gravitational theories and certain quantum field theories developed by Juan Meldacena in 1997, implied that information was indeed preserved. The black hole was not destroying information. It was scrambling it, encoding it in the Hawking radiation in an extraordinarily complex and apparently random way. The information comes back out, but time reversed. The information that falls into the black hole over the long history of its formation and growth comes out in the Hawking radiation in a scrambled, reversed form. In a very deep sense, the physics of black hole evaporation is a physics of time reversal. The information that falls forward in time comes back out in a form that is, in a thermodynamic sense, reversed, maximally randomized, but nonetheless present and in principle recoverable. The physicist Leonard Susskind, who argued against Hawking and won, has written and spoken extensively about what he calls the holographic principle, the idea that the information content of a three-dimensional volume of space can be encoded on its two-dimensional boundary, like a hologram. This principle, which has its deepest mathematical expression in the AD/CFT correspondence, suggests that the universe might be, in some sense, a holographic projection, that the full three-dimensional reality we experience might be an image cast by information encoded on a two-dimensional surface. And this holographic encoding is deeply connected to the thermodynamics of time. The entropy of a black hole, and by extension, the entropy of any region of spacetime, is proportional to the area of its boundary surface, not to its volume. This is the Bekenstein-Hawking formula, and it is one of the most important results in modern theoretical physics. All of this converges on a picture in which time, entropy, information, and the structure of spacetime are not separate phenomena but aspects of a single, deep, as yet not fully understood unity. The arrow of time is not just about the second law of thermodynamics. It is about the structure of quantum gravity. It is about the holographic nature of the universe. It is about the information content of the vacuum of space. And it is about something that we might only begin to fully understand when we have a complete theory of quantum gravity, a theory that does not yet exist. Now let us talk about the human experience of time, and specifically about those moments when our ordinary experience of time's direction seems to fracture or bend. Because these moments are real, documented, and deeply revealing. The most dramatic and well-documented alterations of the subjective experience of time occur in extreme situations. Near-death experiences, certain states induced by meditation, extreme danger, certain psychedelic substances, and specific neurological conditions. And what is striking about many of these accounts is that they involve a profound disruption of the normal sense of time's directionality, a sense of time slowing, stopping, or even reversing. The phenomenon known as time slowing in moments of extreme danger has been extensively documented. People who have survived falls, car accidents, or other near-death experiences very commonly report that time seemed to slow dramatically in the moments before impact. A car accident that lasted a fraction of a second is experienced as unfolding slowly over what seems like many seconds. This is not, as it is sometimes supposed, a sign that the brain is actually processing information faster than normal. Experiments by David Eagleman and his collaborators have shown that the brain does not actually process information faster in these moments. Instead, it is a retrospective reconstruction. The heightened emotional arousal of the crisis causes the brain to encode the experience in unusually rich detail, and when this detail is later recalled, it is experienced as having taken longer than it did. But there are other, more disturbing alterations of temporal experience. The philosopher William James, writing in 1890, described cases of temporal disruption in depression, mania, and extreme psychological states. In severe depression, time can seem to slow to an almost complete halt, each moment becoming an eternity of suffering. In mania, time accelerates, and the normal spacing of events collapses into a rushing torrent. In certain psychotic states, the distinction between past and future can become blurred or reversed. Patients have reported feeling as though effects were preceding causes, as though they were experiencing the consequences of things that had not yet happened. The philosopher Husserl, in his Phenomenology of Time Consciousness, identified what he called the retention and pretension structure of temporal experience. The way in which each present moment carries within it a fading trace of the immediate past, retention, and a leaning forward into the immediate future, pretension. It is this three-part structure, retention, now pretension, that gives our experience its temporal flow, its sense of moving from past to future. And it is precisely this structure that breaks down in temporal disorientation. When you cannot remember the immediate past and cannot anticipate the immediate future, when the retention and pretension are disrupted, the experience of time flowing in a particular direction collapses. You are left in what might be called an eternal, undirected present, neither going forward nor backward, but simply existing in a kind of temporal void. Some of the world's great contemplative traditions, interestingly, have made the dissolution of ordinary temporal experience the goal of their practice. In certain forms of Buddhist meditation, the aim is to enter a state called timelessness, a state in which the ordinary sense of being a self moving through time from past to future dissolves, and what remains is a bare awareness without temporal location. The neuroscientist and philosopher Francisco Varela, who worked on the connections between phenomenological philosophy, cognitive science, and Buddhist meditative experience, argued in his book The Embodied Mind that this dissolution of the sense of temporal flow reveals something important about the constructed, fabricated nature of our ordinary experience of time. The sense of time flowing is not a direct perception of physical reality. It is a construction, an active, ongoing act of interpretation performed by the brain. And like any construction, it can break down, be disrupted, be seen through. This is a profound thought. The experience you have right now of sitting in time, of having a past behind you and a future ahead, of moving from moment to moment in a single direction, this experience is not a direct readout of cosmic temporal physics. It is a model. It is a story your brain tells you. And the physics of time, as we have seen, is strange enough that the story your brain tells is, at best, an extremely useful approximation, one that works beautifully in the thermodynamic middle ground of everyday human experience, but that breaks down at the cosmic scales of the Big Bang in the far future, and at the quantum scales of individual particles, and at the extremes of gravitation near black holes. You are, right now, embedded in a time story, a narrative of flowing from past to future, from cause to effect, from birth toward death. And that story is built on a physical substrate, the thermodynamic arrow of time, that is itself built on an initial condition of the universe that remains deeply mysterious. Now let us turn to something that has occupied science fiction writers and serious physicists alike, the question of time travel. Because the question of what happens if time flows backward is intimately connected to the question of whether it is possible to travel backward in time, to revisit the past, to change what has already happened, to experience the reversed arrow of time as a journey rather than a sudden cosmic transformation. General relativity, Einstein's theory of gravity, is actually remarkably permissive about time travel. The theory contains exact mathematical solutions that have been known since the 1940s, that allow for what are called closed time-like curves, paths through space-time that loop back on themselves, so that a traveler following such a path would return to their own past. The first such solution was discovered by the logician and mathematician Kurt Gödel. Yes, the same Gödel who proved the incompleteness theorems in 1949. Gödel was a close friend and walking companion of Einstein at the Institute for Advanced Study in Princeton, and he gave his time travel solution to Einstein as a birthday present. Einstein was disturbed by it. He acknowledged that the mathematics was correct but expressed discomfort about its implications. Subsequent physicists discovered many other solutions to Einstein's equations that contain closed, time-like curves. The physicist Kip Thorne, who won the Nobel Prize in Physics in 2017 for his work on gravitational waves, showed in 1988 that certain configurations of exotic matter with negative energy density could, in principle, hold open a wormhole, a tunnel through spacetime, and that a wormhole with one end moving at high speed relative to the other could become a time machine, with one end emerging in the future and the other in the past. Thorne's paper, published in the prestigious journal Physical Review Letters, was explicitly titled Wormholes, Time Machines, and the Weak Energy Condition. And it was the work of a physicist of the highest caliber taking the question of time travel with complete seriousness. The key obstacle, Thorne noted, was the exotic matter requirement. Creating and sustaining the negative energy densities needed to hold a wormhole open would require forms of matter and energy that have not been observed in nature, and that might not exist in the quantities needed. The Casimir effect, a real, experimentally measured quantum phenomenon in which parallel metal plates in a vacuum attract each other due to vacuum fluctuations, produces tiny regions of negative energy density between the plates. But the amounts are orders of magnitude too small to hold open a traversable wormhole. Whether the universe permits the exotic matter required for traversable wormholes in sufficient quantities remains an open question. Stephen Hawking, who initially believed that closed time-like curves might be realizable in principle, later proposed what he called the chronology protection conjecture. The hypothesis that the laws of physics conspire to prevent the formation of time machines, precisely because of the logical and physical paradoxes that time travel would create. His argument was based on calculations showing that quantum fluctuations would become infinitely amplified near the moment when a wormhole becomes a time machine, potentially destroying the wormhole, and thus the time machine, just before it became functional. However, Hawking could not prove this conjecture rigorously, and it remains unproven. It is, as Hawking himself noted with his characteristic dry wit, a matter of experimental evidence, based on the fact that we have not been visited by tourists from the future, which, while suggestive, is not exactly a rigorous proof. The physicist Paul Davies, in his book How to Build a Time Machine, presents a thoughtful and genuinely scientific exploration of the possibilities and obstacles. Davies notes that the grandfather paradox, the famous logical contradiction in which you travel back in time and kill your grandfather before your father is conceived, thus preventing your own birth and therefore your own time travel, is not necessarily fatal to the idea of time travel. Various resolutions have been proposed. The Novikov self-consistency principle, developed by the Russian physicist Igor Novikov, states that any attempt to change the past would fail, not because the physics forbids the attempt, but because the attempt itself is part of what already happened. In a self-consistent closed time-like curve, there is only one history, and it is internally consistent. The many worlds interpretation of quantum mechanics offers a different resolution. Time travel to the past takes the traveler into a different branch of the quantum multiverse, not back into their own past. So the grandfather is killed in a parallel timeline, not in the traveler's own. The traveler's home timeline is unchanged. These are not idle speculations. They are the results of serious, mathematically rigorous analysis by professional physicists publishing in peer-reviewed journals. The question of time travel is taken seriously at the frontier of theoretical physics because it is connected to some of the deepest issues in physics. The nature of space-time, the global structure of general relativity, the relationship between quantum mechanics and gravity, and the ultimate fate of causality as a fundamental principle. Now let us talk about something that is simultaneously simpler and stranger than anything we have discussed so far. Let us talk about the everyday evidence that time's arrow is not as fundamental as it seems. Consider this. When you look at the night sky and see a star, you are not seeing that star as it is now. You are seeing it as it was years, centuries, or millennia ago, depending on its distance. Light travels at a finite speed, approximately 300,000 kilometers per second, and the light from distant stars left those stars long before you were born. The universe you see around you at any moment is not a simultaneous cross-section of cosmic reality. It is a temporal mosaic, a patchwork of images from different times, each one a message from the past arriving in your present. Some of the stars you see in the night sky may not exist anymore. They may have exploded in supernovae, or collapsed into black holes, or simply burned out. And we will not know for decades, centuries, or millennia, because the light carrying that information has not reached us yet. We are, in a very real sense, surrounded by the past. We live in the present moment, but we are bathed in light from the past. The universe is, visually, a time machine. Looking out into space is the same as looking back into time. And the further you look, the further back you see. The most distant objects visible to modern telescopes, galaxies at redshifts greater than 10, observed by the James Webb Space Telescope, which began its scientific operations in 2022, are being seen as they were less than 500 million years after the Big Bang. We are looking at infant galaxies, the earliest structures in the universe, forming from the primordial clouds of hydrogen and helium left by the Big Bang. We are seeing the universe's childhood. And the absolute limit of this backward vision is the cosmic microwave background radiation, the thermal afterglow of the Big Bang itself, light emitted about 380,000 years after the beginning of the universe, which has been traveling through space ever since and which we can detect today as a faint, all-pervasive microwave radiation filling the entire sky. The cosmic microwave background is the oldest light in the universe. It is a direct image of the universe when it was extraordinarily young, extraordinarily hot, and extraordinarily smooth, in its early state of low entropy. It is, in the most literal sense, a photograph of the universe's beginning, and studying it in detail, as the COBE satellite did in the 1990s, as the WMAP satellite did in the 2000s, as the Planck satellite did in the 2010s, has given us an extraordinarily precise picture of the initial conditions of our universe. The temperature fluctuations, the density variations, the seeds from which all cosmic structure would eventually grow. And here is what those observations tell us. The early universe was smooth, almost perfectly uniform. The temperature of the cosmic microwave background is the same in every direction of the sky to 1 part in 100,000. An extraordinary degree of uniformity. But it is not perfectly uniform. There are tiny fluctuations, tiny variations in temperature and density that were imprinted on the universe in its first fractions of a second by a process called cosmic inflation. Inflation, a period of extraordinarily rapid exponential expansion in the first tiny fraction of a second after the Big Bang, smoothed out the universe on large scales while amplifying tiny quantum fluctuations into the density variations that would eventually become galaxies, clusters of galaxies, and the vast cosmic web of filaments and voids that we observe today. The theory of inflation was developed by the physicist Alan Guth in 1980, building on earlier work by Alexei Starobinsky and others. It has become a cornerstone of modern cosmology, and while many specific models of inflation are still debated, the broad picture has received extraordinary observational support from the precise measurements of the cosmic microwave background. In 2014, the BICEP-2 collaboration announced what they believed was direct evidence of gravitational waves produced by inflation, ripples in spacetime generated by the violent exponential expansion of the early universe. The announcement was subsequently shown to be contaminated by signals from dust in our own galaxy, but the search for primordial gravitational waves continues, and many physicists believe that future experiments will detect them. What does inflation have to do with the arrow of time? Quite a lot, actually. Inflation is one of the most plausible physical mechanisms for explaining why the early universe was in such a low entropy state. If the universe began in a generic high entropy state, inflation would have driven it toward the smooth, uniform state that we observe, not by decreasing entropy globally, but by expanding the universe so rapidly that the entropy per volume decreased, even as the total entropy increased. Inflation generates the low-entropy initial conditions of our observable universe not by miracle or by fine-tuning, but by physics, by the exponential expansion of spacetime driven by the energy of a hypothetical scalar field called the inflaton. But inflation itself raises deeper questions. What drove inflation? What was the inflaton field? How did it begin? And, most relevantly for us, was inflation itself the ultimate source of the arrow of time, or was it just one step in a longer chain of causation that must ultimately be traced back to something even more fundamental? These questions lead us to the very frontier of theoretical physics. They lead us to string theory, to loop quantum gravity, to causal dynamical triangulations, to other approaches to quantum gravity that are still in development. They lead us to the question of whether time itself is fundamental, or whether it is an emergent phenomenon, something that arises from a deeper, timeless substrate. The physicist Carlo Rovelli, one of the founders of loop quantum gravity and the author of the beautiful popular book The Order of Time, argues that time is not fundamental. In Rovelli's picture, the fundamental description of the universe, at the level of quantum gravity, does not contain time. It contains a network of quantum states connected by quantum transitions, and what we call time is an emergent, approximate, effective description that appears when you look at this network from a sufficiently coarse-grained perspective. The flow of time, the arrow of time, the distinction between past and future. All of this is, in Rovelli's view, something that emerges from the statistical mechanics of a timeless underlying quantum gravity, not something that is built in at the most fundamental level. Rovelli's view is controversial and contested, but it is taken seriously by many physicists. And it leads to a picture in which asking, what if time flowed backwards, is, in a sense, asking about the wrong level of description. At the fundamental level, there is no time flowing in any direction. There is just a quantum network of states and transitions, governed by timeless equations. Time's flow, and with it time's direction, is something that we project onto this network, something that emerges from our particular thermodynamic situation within it. Change the situation, and you change the time. Reverse the situation, and you reverse the time. The timeless laws are indifferent. Now let us do something that physics alone cannot do. Let us be human for a moment. Let us talk about what the reversal of time means for love, and grief, and memory, and the human experience of loss. In our world, love unfolds forward in time. You meet someone. You get to know them. You build a history together. The history accumulates. Shared experiences, private jokes, mutual understanding, the texture of a life lived alongside another. And then, if you are lucky, there is also grief, because grief is what happens when someone you love is taken forward through time without you, into a future you cannot follow. Grief is the pain of temporal separation. It is the anguish of being left in the present while the one you loved moves into the permanence of the past. What would love look like in a time-reversed world? What would grief look like? This is not a merely rhetorical question. Think it through seriously. In a time-reversed world, you would meet someone in what is, for them, the last moment of your relationship. You would say goodbye at the moment of meeting. You would then spend time together in reverse, each day undoing the intimacy built the day before, each conversation erasing the understanding gained previously. You would begin as people with a rich, shared history and end as strangers who have never met. Your relationship would move from fullness to emptiness, from closeness to estrangement, from the complexity of a shared life to the simplicity of two unknown individuals. In such a world, would there be grief? And if so, at what moment? Would you grieve at the meeting, the moment of goodbye? Or would the grief come at the parting, the moment when you become strangers again? And crucially, would the grief of a time-reversed being feel the same as ours? Would it have the same quality of longing, the same sense of irrecoverability, the same ache of reaching back toward something that cannot be reached? The philosopher Marcel Proust, in his vast novel In Search of Lost Time, argued that genuine knowledge of the past is accessible not through voluntary memory, the deliberate, intellectual effort to recall, but through involuntary memory, the sudden, unexpected, overwhelmingly vivid recollection triggered by a sensory stimulus. The most famous example is the taste of a madeleine dipped in tea, which suddenly and completely transports Proust's narrator back to his childhood. This involuntary memory is, Proust argues, a kind of time reversal, a genuine reliving of the past, not merely a representation of it. In the moment of involuntary memory, the past is present. Time is reversed. The distance between then and now collapses. Neuroscience has partially explained Proust's insight. The hippocampus and related structures in the medial temporal lobe store episodic memories. memories of specific events in specific times and places, and these memories are intimately linked to emotional and sensory content via connections to the amygdala and other limbic structures. When a sensory stimulus triggers an emotional association, the associated memory can be retrieved with extraordinary vividness and immediacy, flooding consciousness with the past. This is not literally a time reversal, of course, but it is a functional analog, a way in which the neural system that encodes the past can, under the right circumstances, produce an experience of the past that is almost indistinguishable from the experience of the present. There are neurological patients who live, in a sense, in permanent versions of this state. Patients with certain forms of post-traumatic stress disorder experience involuntary, vivid, intrusive memories, flashbacks, that feel not like remembering the past but like re-experiencing the present. In these flashbacks, the distinction between then and now collapses. The patient is not remembering trauma. They are, phenomenologically, living through it again. The arrow of time, the distinction between past experience and present experience, is temporarily erased. The result is not liberation. It is a particular kind of suffering, being trapped in the past, unable to move forward into the present and future. This should give us pause. The arrow of time, the fact that memory is of the past and not the present or future, the fact that we can revisit the past only in representation and not in experience, is not merely a physical convenience. It is a psychological necessity. The ability to distinguish the past from the present is a prerequisite for mental health, for coherent selfhood, for the ability to function in the world. Neurological conditions that blur this distinction, that make the past feel present, are experienced not as freedom but as torment. So when we fantasize about reversing time, about being able to go back, to undo, to have another chance, we should be careful about what we are wishing for. The reversal of time's arrow is not the same as having a second chance. It is something far stranger, far more radical, and potentially far more disorienting than anything our forward time imagination can easily grasp. And yet there is something in the idea that will not let go. There is something profound and persistent in the human longing to reverse time, to undo what has been done, to return to before the loss, before the mistake, before the moment of no return. This longing is, I think, one of the most distinctively human experiences. Animals do not, so far as we can tell, regret the past in the abstract. They respond to immediate stimuli, they learn from experience, they adapt. But the human capacity to reach back in time through memory, to revisit the past with the knowledge of the present, to see what we would have done differently, this is uniquely human. And it is, like all human experiences, a direct consequence of the thermodynamic arrow of time. We remember the past. We can reconstruct it in vivid detail. We can carry it with us into the present. And in doing so, we can feel the gap between what was and what we wish had been. That gap, the distance between the past we remember and the past we wish for, is what makes us long to reverse time. It is the ache at the heart of regret. And it is only possible because we live in a universe where the past leaves traces, where entropy increases, where time flows irreversibly in one direction from lower entropy to higher. In a universe where time ran backward, or where time had no direction at all, regret as we know it would be impossible. You cannot regret what you cannot remember. You cannot wish to change a past that is unknown to you. The very capacity for regret is a gift of the thermodynamic arrow of time. And perhaps this is a speculation, a personal reflection rather than a scientific claim. The value of regret, its function as a guide for future behavior, as a spur to learning and growth and moral development, is also something that depends on time's forward flow. You regret so that you do not repeat. You mourn so that you love more wisely. You carry the past into the future not as a burden but as a teacher. All of this is possible only because time flows one way. Let us now turn to some of the most recent and most exciting scientific developments in the physics of time, because the science is moving fast, and some of the most recent results are genuinely extraordinary. One of the most active areas of research at the frontier of physics right now is the study of quantum information and its relationship to spacetime. The growing field of quantum information theory, which studies how information can be stored, processed, and transmitted in quantum systems, has begun to intersect in profound ways with the physics of gravity and spacetime. In particular, the work of Netta Engelhart at MIT, building on earlier work by Ahmed Almhiri, Netta Engelhart, Henry Maxfield, and Jeff Pennington, has produced what physicists are calling the island formula for black hole entropy. This formula, derived using quantum gravity techniques from the AD/CFT correspondence, provides a resolution of the black hole information paradox, the question of whether information is preserved or destroyed when a black hole evaporates, that is compatible with both quantum mechanics and general relativity. The island formula involves a genuinely remarkable idea, that the entropy of the Hawking radiation emitted by a black hole is not simply the sum of the entropies of the individual radiation quanta, but must include a contribution from a disconnected region of spacetime inside the black hole, an island. This island is connected to the outside radiation region not by any spatial tunnel, but by quantum entanglement, by the deep, non-local quantum correlations between the Hawking radiation and the interior of the black hole. The result is that the entropy of the Hawking radiation follows what is called the Page curve. It increases at first, as the black hole begins to evaporate, but then decreases and ultimately goes to zero when the black hole is completely evaporated, consistent with the preservation of quantum information. Why does this matter for the arrow of time? Because the Page curve is a time-symmetric object. It has a clear beginning and end, and the information that goes in eventually comes out, preserving unitarity. But the process by which it does so is deeply connected to the structure of quantum gravity in ways that are not yet fully understood. The resolution of the black hole information paradox, if the island formula is correct, seems to require a fundamentally new understanding of how geometry and spacetime emerge from quantum information, a picture in which spacetime itself, including its temporal structure, is in some sense constructed from quantum entanglement rather than being a fixed background stage on which quantum processes play out. This is the frontier. This is where the deepest questions about time, its arrow, its nature, its reversibility, are being actively explored. And the researchers working on these questions, Netta Engelhart, Ahmed Almhiri, Don Merolf, Jeff Pennington, Juan Meldacena, and many others, are doing so with the full rigor of modern theoretical physics, publishing in the most prestigious journals, presenting at the most prestigious conferences. These are not marginal ideas. They are central to the contemporary project of understanding what the universe fundamentally is. And at the center of all of it is time, its direction, its origin, its ultimate fate, what it means, what it costs, what it gives us, and what we would lose or gain or become if it ran the other way. Let us spend some time now with a set of questions that bring time reversal into the domain of everyday speculation and imagination. Questions that you can genuinely ask yourself and think about, because they connect the cosmic and the personal in ways that are both illuminating and genuinely unsettling. Here is one. If you knew right now that time's arrow would reverse tomorrow, that entropy would begin to decrease, that the universe would begin to unevolve, that every process would begin to run in reverse, what would you want to do today? Would you try to leave a message for your past self, knowing that the reversed version of your past self would receive it as a memory of the future? Would you try to complete something, finish something, make something that would survive the reversal? Or would you recognize that nothing you made today would survive in any meaningful sense in a reversed universe? That the structures you built would dissolve, the words you wrote would unwrite themselves, the memories you formed would unfold back into the stimuli that created them? There is something poignant about this question. We live in a forward-time universe, and everything we make, everything we say, everything we do is built for forward time. Books are written to be read in sequence. Buildings are built to stand. Relationships are built on accumulated history. Art is made to endure. All of this, every act of human creation, is a bet on the continuation of the arrow of time, a wager that the forward-flowing universe will continue to flow forward, that the structures we build will persist into a future that follows from the present. A reversal of time's arrow would not merely end these projects. It would unmake them. And this, I think, is the deepest horror lurking in the idea of time reversal. Not the physical strangeness of heat flowing backward or ripples converging inward, but the existential horror of everything you have made, everything you have meant, everything you have loved, being unmade. Not destroyed, not erased, unmade. Wound back, unpieced, returned to the formless possibility from which it came. This is not so different from what death does. Death is, in thermodynamic terms, the ultimate victory of entropy, the breakdown of the complex, improbable, ordered structure of a living organism back into simpler molecules, eventually into atoms, eventually into a diffuse cloud of particles that will never again spontaneously reassemble into anything like what they were. Death is irreversible, not because any physical law demands it, but because the probability of spontaneous reassembly is so astronomically small that it effectively never happens. In this sense, every death is a small, local arrow of time, a miniature one-way transition from high complexity to high entropy, embedded in a universe that is doing the same thing on the cosmic scale. And the arrow of time gives death its sting, but it also gives life its meaning. It is because the past is irreversible, because you cannot go back, cannot undo, cannot unlive what has been lived, that each moment has weight. Each decision matters. Each loss is real. The irreversibility of time is not a flaw in the architecture of the universe. It is the condition that makes everything matter. This is something that the great physicist Richard Feynman understood deeply and articulated with characteristic vividness. Feynman, who had witnessed profound loss, his first wife Arlene died of tuberculosis when he was very young, during the Manhattan Project, understood time's irreversibility not just as a physicist but as a man. He wrote a heartbreaking letter to Arlene after her death, beginning, "I love my wife. My wife is dead." He kept the letter sealed for years, and only opened it at the very end of his own life. It is one of the most human things he ever wrote, and it is saturated with the ache of irreversibility, with the knowledge that what is gone cannot be recovered, that the past is permanent even as the future is open, that love and loss exist only because time flows in one direction. If time flowed in reverse, Arlene would undie. She would grow younger. She would unbe ill. And eventually she would unbe, as would Richard, as would all of us, dissolving backward into the unborn, the unconceived, the unimagined. In a time-reversed universe, there would be no Richard Feynman, no Nobel Prize, no path integrals, no beautiful curiosity. Just as in our universe, the eventual heat death of the cosmos means that there will be no Feynman in the far future. No memory of him, no trace of what he thought or felt or loved. Time's arrow, running forward, gives us Feynman for a moment and then takes him away. Running backward, it would never have given him to us at all. This is perhaps the most philosophically arresting fact about time reversal. It does not merely change the direction of events. It changes the entire narrative of existence. Our universe, running forward, is a story of increasing complexity. Of simple atoms becoming stars, stars becoming heavier elements becoming planets, planets becoming life, life becoming consciousness, consciousness becoming science and art and love and grief. A time-reversed universe is a story of decreasing complexity, of consciousness dissolving into life, life dissolving into chemistry, chemistry dissolving into atoms, atoms dissolving into the undifferentiated energy of an infinitely smooth, infinitely uniform, maximally entropic cosmos. That is not a story. That is the anti-story, the unstory. And we, you and I, and everyone who has ever lived, are characters in the story, not the anti-story. We are creatures of the forward time arrow, and everything that makes us what we are, our consciousness, our memory, our love, our creativity, our science, our suffering, our joy, is written in the language of increasing entropy, of the thermodynamic arrow that Eddington identified and Boltzmann died defending. So what would happen if time began flowing backwards? The full answer is this. At the physical level, entropy would begin to decrease. Complex structures would spontaneously form from simpler ones. Stars would unburn. Life would undie and then unlive. The universe would become more organized, more constrained, more thermodynamically exceptional, marching backward toward the low entropy state of its beginning. At the biological level, organisms would reverse their aging. Wounds would unheal in reverse, or rather, they would heal before being wounded. Death would run backward into life. At the cognitive level, memory would flip. The future would be known, the past unknown. Causality would appear to run from future to past. Communication and cooperation would become impossible across the temporal divide between forward and reversed observers. At the human level, love would begin as history and end as estrangement. Grief would dissolve as the lost returned. Regret would become anticipation. Meaning would not disappear, but it would be radically restructured, rewritten in the reversed language of decreasing entropy, of the anti-story, of a universe winding back toward its beginning. And at the deepest level, at the level of physics, philosophy, and the nature of existence itself, the reversal of time's arrow would reveal what the arrow always was. Not a fundamental feature of the laws of nature, but an emergent consequence of initial conditions. The universe's temporal direction is not decreed by any deep physical principle. It is an accident, an extraordinarily improbable, cosmically specific, deeply beautiful accident. An accident that gave us stars and life and consciousness and Beethoven and grief and the smell of rain on warm pavement and the taste of a Madeleine dipped in tea and the image of a parent holding a child and the equations that Boltzmann died defending and the letter that Feynman could not bring himself to open. An accident that gave us time, given to us not by decree but by the extraordinarily low entropy of a moment we call the beginning, running irreversibly forward through the cosmic dark, carrying everything with it. Now here is something that deserves very careful thought, and I want you to sit with it. When physicists talk about the heat death of the universe, the far future state in which entropy has reached its maximum, in which all stars have burned out, all black holes have evaporated, all matter has decayed, and the universe is a cold, thin, maximally disordered gas of photons and neutrinos expanding forever, they are describing the ultimate triumph of the arrow of time. Entropy, having been low at the beginning, has run all the way to the maximum. There is nowhere further for it to go. The second law of thermodynamics has been, in a sense, fully satisfied. It has done its work. And in that state, in the asymptotic far future of our universe, there would be no arrow of time. Not because time would be reversed, but because in a maximum entropy state, every direction of time is the same as every other. There are no low entropy states to return to, no high entropy futures to move toward. Entropy is already at the maximum everywhere. The second law of thermodynamics is trivially satisfied in both temporal directions, because there is no direction in which entropy could increase. It is already as high as it can be. The arrow of time, the thing that drives all change, all process, all becoming, would simply cease to exist. In the far future of our universe, if the cosmological constant remains constant and the universe continues its accelerating expansion, the heat death would arrive in something like 10 to the power of 100 years, a number so large that all of recorded history occupies a time interval that is not even a rounding error by comparison. Every star, every galaxy, every atom of ordinary matter will have undergone every possible physical process many times over. And what remains will be a thin, cold, maximally disordered soup in which time has no direction, because nothing changes in any consistent way. There is no past lower in entropy than the present, because there is no structure left to have low entropy. There is no future higher in entropy than the present, because entropy is already at the maximum. In that state, there are no observers. There is no consciousness. There is no memory. There is no love or grief or curiosity or wonder. There is just the vast, cold, undirected, aimless thermodynamic equilibrium of a universe that has completed its forward journey and arrived at the end of the arrow of time. Not time reversed. Not time stopped. Just time, directionless, meaningless, continuing perhaps as a mathematical parameter but no longer as anything experienced or remembered or felt. This is the universe's ultimate fate, as best as current physics can project. and it should make you feel something. Not merely intellectual interest, but something more immediate and more visceral. Because you are alive right now, at this particular moment in cosmic history, when entropy is still low enough that stars shine and life exists and consciousness arises and asks these questions. You are alive in the early, structured, arrow-directed phase of the universe's existence. You are a child of the arrow of time, living in the brief cosmic morning before the long, dark, directionless afternoon of the universe's far future. The arrow of time is not just a physics fact. It is the condition of your existence. And its possible reversal is not just a physics puzzle. It is a meditation on what it means to exist, to be embedded in time, to move in one direction through a universe that might, in principle, move in any direction at all, and to find meaning and love and suffering and beauty in the extraordinarily improbable arrow of time that our universe, for reasons we do not yet fully understand, was given at its birth. Now, there is one more territory we need to explore before we can feel the full weight of this question. And that territory is the most personal one of all. It is the territory of aging. We age because entropy increases. This is not a metaphor. It is a precise, rigorous, biologically and thermodynamically well-supported statement. The aging process is, at the cellular level, a process of accumulated damage. DNA damage, protein misfolding, telomere shortening, mitochondrial dysfunction, cellular senescence. These processes are all, at the deepest level, consequences of the thermodynamic arrow of time. Of the fact that complex, organized biological structures exist in a universe of increasing entropy and are gradually degraded by the same thermodynamic forces that degrade everything else. But the specific mechanisms of aging are also the subject of intense scientific research, because aging is not just philosophically interesting, it is medically and practically important. The longevity researcher Aubrey de Grey, the molecular biologist Elizabeth Blackburn, who won the Nobel Prize for discovering telomerase, the cellular biologist David Sinclair, who studies NAD metabolism and sirtuins. All of these researchers are working on what amounts to, at the biological level, a project of locally reversing the arrow of time. Not cosmically, not globally, but in the specific, limited domain of cellular and molecular aging. They are trying to undo the accumulated entropic damage in biological cells, to return cells to a younger, lower entropy state, to, in a very specific biological sense, make time run backward for the cells of a living body. And they have had some success. In model organisms like worms and flies and mice, researchers have extended lifespan dramatically, sometimes by factors of 2 or 3, by manipulating specific genetic and metabolic pathways. Genes in the insulin signaling pathway, when mutated in certain ways, can dramatically extend the lifespan of worms. Caloric restriction, eating significantly less than ad libitum, extends lifespan in a wide variety of organisms, from yeast to flies to mice, and there is evidence that it does the same in primates and possibly in humans. The drug rapamycin, which inhibits a cellular signaling hub called mTOR, extends lifespan in mice even when administered in old age. These are real, reproducible, peer-reviewed scientific results. More recently, researchers have shown that it is possible to reprogram adult cells back to a pluripotent state, essentially erasing the epigenetic marks of aging and returning the cell to a younger state, using the Yamanaka factors, a set of transcription factors identified by the Japanese researcher Shinya Yamanaka, who won the Nobel Prize in Physiology or Medicine in 2012 for this work. Partial reprogramming, applying the Yamanaka factors transiently rather than completely, has been shown in animal experiments to reverse aspects of cellular aging without causing the cells to lose their differentiated identity. This is as close as biology has yet come to a genuine biological time reversal, a literal reversal of the epigenetic arrow of aging at the cellular level. Is it possible, in principle, to reverse aging completely? To restore an old organism to a young state? The honest answer is that we do not know. The theoretical obstacles are formidable. The body is not just a collection of cells. It is a complex, interdependent system in which cells, tissues, organs, and physiological systems interact in ways that are extraordinarily difficult to restore once they have been disrupted. The brain, in particular, may be especially difficult to rejuvenate. The connections between neurons, the synaptic architecture that encodes your memories, your personality, your accumulated experience, are themselves products of the aging process. Restoring youth to the brain cells while preserving its cognitive content may be impossible in principle, or may require a degree of precision and control that we are very far from achieving. But the direction of the research is clear, and the momentum is substantial. The global longevity research community is growing rapidly, funded by some of the wealthiest individuals and institutions in the world. Companies like Calico, funded by Alphabet and Unity Biotechnology, and Altos Labs, where David Sinclair, Juan Carlos Espizua Belmonte, and other leading aging researchers work, are investing billions of dollars in the project of understanding and ultimately reversing the biological arrow of aging. Whether they will succeed, and in what time frame, is a question that no one can answer with confidence. But the attempt is being made, with unprecedented resources and scientific sophistication. And if they succeed, if biological aging is reversed, it will be one of the most extraordinary things that has ever happened in the history of life on Earth. Not because it would make people immortal, there are many other ways to die besides aging, but because it would represent a genuine, practical, biological reversal of a major component of the local thermodynamic arrow of time. It would be a demonstration that entropy's increase is not an inescapable destiny but a local tendency that can, with sufficient intelligence and energy expenditure, be locally counteracted. This is not without precedent. Life itself is already a local counteraction of entropy. Every living organism is a structure that maintains and increases its internal order by consuming energy from its environment and exporting entropy to its surroundings. A cell is a machine for locally decreasing entropy by doing work, by using the chemical energy of food or sunlight to build complex molecules, maintain organized structures, and drive orderly processes. This does not violate the second law of thermodynamics, because the entropy exported to the environment always exceeds the entropy decrease within the organism. But it does demonstrate that local reversals of the entropic arrow are not only possible but are, in fact, what all of life has been doing for the past 3.5 billion years. We are, all of us, local victories over entropy. We are islands of order in a sea of increasing disorder. We are, in a very real thermodynamic sense, swimming against the current of the arrow of time. Not reversing it, but creating, for a brief moment in the cosmic story, pockets of complexity and order and consciousness that the universe's thermodynamic arrow would otherwise not allow. And consciousness itself, the thing that allows you to hear these words, to wonder about these questions, to feel the full weight of what time and its reversal mean. Consciousness is perhaps the most extraordinary local reversal of entropy that the universe has produced. The human brain contains approximately 86 billion neurons, each connected to thousands of others through a network of synapses of almost incomprehensible complexity. The information processing capacity of this network, the ability to perceive, to remember, to think, to imagine, to feel, is a form of order so extraordinary that it has no parallel in the non-living universe. And it is maintained, moment by moment, by the metabolism of the brain cells, by the constant consumption of oxygen and glucose, by the constant export of heat to the environment, by the constant thermodynamic work of keeping the neural network far from equilibrium. Your consciousness is a thermodynamic achievement. Your ability to wonder about time's reversal is itself a consequence of the forward arrow of time. The very curiosity that drives you to ask these questions, the ability to hold a question in mind, to think about it from multiple angles, to feel the vertigo of possibilities, is made possible by the fact that your brain is a living, metabolizing, entropy-exporting, order-maintaining miracle of biological evolution. And that miracle was produced by the forward arrow of time, by 4 billion years of natural selection in a universe where entropy increases and complex structures accumulate over time. If time had flowed backward from the moment of the Big Bang, none of this would exist. Not you. Not consciousness. Not the question itself. The question, what if time began flowing backwards, can only be asked by a creature of the forward arrow. It is a question that the universe asks of itself through the medium of creatures that the forward arrow produced. This is the last and deepest thing I want to say about time reversal. Not the physics, as extraordinary as the physics is. Not the philosophy, as vertiginous as the philosophy is. Not the neuroscience, as illuminating as the neuroscience is. But this, the question of time's direction, is ultimately a question about why you are here at all. Why there is something rather than nothing. Why the universe produced observers who can wonder about their own existence. Why entropy was low at the beginning. Why the arrow of time points in the direction it does. These are the deepest questions that science and philosophy have ever asked. And they do not yet have complete answers. But they have partial answers, and those partial answers are extraordinary. They tell us that we live in a universe that is thermodynamically extraordinary. Born in a state of improbable order, evolving toward disorder, producing along the way the complexities of stars and planets and life and consciousness and love and grief and science and wonder. They tell us that the arrow of time is the condition of everything we are and everything we value. They tell us that the reversal of that arrow would not be merely a physical oddity but an existential catastrophe. Or perhaps, from the perspective of a being embedded in the reversed arrow, an existential miracle. They tell us that time is both more fragile and more profound than we ever suspected. Not a fixed cosmic river, but an emergent thermodynamic phenomenon, balanced on the extraordinarily improbable initial conditions of a universe that might, in principle, have been otherwise. And they leave us here, at this moment, in the forward arrow of our forward time universe, with everything that implies. With memory and anticipation, and the knowledge that what has passed cannot be recovered, and that what has not yet happened is genuinely open, genuinely uncertain, genuinely ours to shape. This moment, right now, this exact moment, is the only moment that is simultaneously not yet past and not yet future. It is the razor's edge of the arrow of time. The place where cause becomes effect, where possibility becomes actuality, where the future collapses into the present and the present falls into the past. It is, in the most literal sense, where you live. Think about that. Think about the fact that you are always and only at the exact point where the arrow of time is actively doing its work, transforming the low entropy past into the higher entropy future, one moment at a time. You are not watching the arrow of time from a safe distance. You are living it. You are made of it. You are, in the most intimate and unflinching sense, a creature of the forward arrow, born of it, sustained by it, and inevitably, irreversibly, taken by it. Now, let us push into something that recent theoretical physics has raised with genuine urgency. The possibility that what we experience as the present moment, the now, may itself be an illusion, or at the very least, a highly misleading simplification of what is actually happening at the fundamental level. In Einstein's relativity, as we noted earlier, there is no universal present. There is no cosmic clock that all observers agree on. The present, the instant we call now, is not a global fact about the universe. It is a local, observer-dependent, reference frame-dependent notion. Two events that are simultaneous in one reference frame are not simultaneous in another. This is not a philosophical nicety. It is an experimentally confirmed fact. The relativity of simultaneity has been tested to extraordinary precision using atomic clocks on aircraft and satellites, using particle accelerators, using 100 years of accumulated experimental evidence. It is as well established as any fact in physics. And if the present is not a universal fact, then the flow of time, the sense of now moving forward from past to future, is also not a universal fact. It is a local, observer-dependent experience. The philosopher of physics Christy Miller, in her work on the metaphysics of time, explores what this means for our intuitive sense of temporal passage. The sense that time does not merely exist in 4 dimensions but actively flows, that the now actually moves from earlier to later. Miller and her collaborators argue that this sense of flow is not captured by the static, 4-dimensional space-time picture of physics, the so-called block universe, in which all moments of time exist equally, past, present, and future, laid out in a 4-dimensional manifold without any privileged, now, moving through them. In the block universe, time does not flow. All moments simply exist, statically, eternally. The block universe picture is the natural consequence of taking Einsteinian relativity seriously. If there is no universal present, then there is no universal now to mark the boundary between the determined past and the open future. All events exist with equal ontological status in the four-dimensional space-time manifold. Your birth and your death both exist, equally real, separated by time rather than by existence. Nothing comes into being or passes out of being. Everything simply is, located at its particular coordinates in space-time. This is a deeply counterintuitive picture, and many philosophers resist it on the grounds that it eliminates the very thing that seems most fundamental about our experience of time: its passage. The philosopher of time A.N. Prior argued passionately for the reality of temporal passage, for the genuinely irreducible truth of statements like, "It is now Tuesday," and "Yesterday is past and tomorrow is yet to come." Prior developed a formal logic of time, tense logic, to capture these truths in a rigorous way. And he maintained that the block universe picture, by eliminating the reality of the present moment, failed to capture something essential about the nature of time as it is actually experienced. The debate between the block universe view and the view that takes temporal passage seriously, sometimes called the A theory versus B theory debate in philosophy of time, has been going on for over a century, and it is not resolved. But it is directly relevant to the question of time reversal, because if the block universe is correct, then time flowing backwards is not even a well-defined possibility. In the block universe, time does not flow at all. There is no direction of flow to reverse. There are simply the temporal relations of earlier than and later than between events, and these relations are fixed, eternal, and unchangeable. The future is as real as the past as real as the future, and the question of reversing the flow of time is, in a sense, category confusion, asking what would happen if something that does not flow began flowing in the opposite direction. But if the A theory is correct, if temporal passage is real, if the present moment is genuinely privileged, if there is something that genuinely comes into being and passes out of being as the now moves forward, then the question of time reversal has a clear meaning, and the reversal would be a genuine cosmic transformation. The now would begin moving in the opposite direction, from future to past rather than from past to future, and everything that follows would be everything we have. Described in this conversation, the philosopher Tim Maudlin, one of the most rigorous and penetrating thinkers in the philosophy of physics, argues that the block universe picture is not entailed by relativity, and that relativity is compatible with a robust form of temporal passage, provided that the passage is understood in a way that does not require a universal present. In Maudlin's picture, time has an intrinsic direction. It is not merely a fourth dimension symmetric with the three spatial dimensions. It is a directed dimension, with a genuine distinction between past and future built into its fundamental structure. And this direction is not merely a thermodynamic artifact, not merely a statistical tendency, but something real and fundamental about the nature of temporal reality. Maudlin's view is contested, but it is philosophically serious and carefully argued. And it aligns with the intuitions of many physicists who feel that the block universe, whatever its mathematical elegance, fails to capture the dynamism and directionality of the physical world as we actually experience and study it. So what do we actually know? And what remains genuinely unknown? We know that the fundamental laws of physics, at the level of classical mechanics, quantum mechanics, and general relativity, are largely time-symmetric. We know that the second law of thermodynamics gives time a direction, but that this direction is statistical rather than absolute, and depends on the extraordinarily low entropy of the universe's initial state. We know that quantum mechanics has certain time asymmetric features, particularly in the measurement process and in the decay of certain particles, but that the nature and significance of these asymmetries is still debated. We know that the arrow of time is directly connected to the origin of the universe, and that explaining the arrow requires explaining why the Big Bang was in such an improbable low-entropy state. We know that time reversal in quantum mechanics is experimentally realizable for small systems, using the computational resources of quantum computers, but that macroscopic time reversal is effectively impossible because of the overwhelming thermodynamic statistics. We do not know why the Big Bang had such low entropy. We do not know whether the multiverse is real, and whether it could explain the low-entropy initial state of our universe. We do not know whether time is fundamental or emergent. We do not know what the correct interpretation of quantum mechanics is, and therefore we do not know how to understand the time asymmetric aspects of quantum measurement. We do not know whether closed time-like curves are realizable in nature, or whether the chronology protection conjecture is correct. We do not know whether the arrow of time will persist into the far future of the universe, or whether some future phase transition, some cosmological event we cannot currently predict, could reverse or eliminate it. These are genuine, open, frontier questions in physics and philosophy. They are being actively investigated by brilliant researchers at the leading institutions of the world. And while we do not know the answers, the investigation of these questions has already produced some of the most beautiful and profound science of the past century. From Einstein's relativity to Boltzmann's statistical mechanics, from the discovery of the cosmic microwave background to the AD/CFT correspondence, from the experimental verification of quantum non-locality to the tentative resolution of the black hole information paradox. The question of what would happen if time began flowing backwards is, ultimately, the question of what time fundamentally is. And the answer to that question, which we are still working toward, with the most powerful mathematical tools and the most sophisticated experimental techniques that human civilization has produced, will be one of the deepest insights that science has ever achieved. It will transform our understanding of the universe, of consciousness, of the nature of causality, and of what it means to exist. But right now, in this moment, before we have that complete answer, we have something equally valuable. We have the question. We have the wonder. We have the vertigo of standing at the edge of what is known and peering into the unknown, knowing that the unknown is real and vast and full of truths that would change everything if we could only reach them. And we have the arrow of time pointing forward, carrying us from this moment into the next, from curiosity into knowledge, from question into answer, or perhaps into a deeper question still. Think about water flowing downhill. It seems so natural, so inevitable, so obvious. Of course water flows downhill. Gravity pulls it there. But a physicist will tell you that downhill is not a fact about the water itself. It is a fact about the gradient, the difference in potential energy between where the water is and where it could be. Remove the gradient, and the water does not know which way to flow. It meanders randomly, or it sits still in equilibrium. Time is like that water. The arrow of time, the sense of it flowing forward, inevitably and irreversibly, is not a fact about time itself. It is a fact about the gradient. The thermodynamic gradient between the low entropy past and the higher entropy future. Remove the gradient. Get the universe to a state of maximum entropy, and time does not know which way to flow. It ceases, effectively, to flow at all. The arrow vanishes, not because it was reversed, but because there is no longer any thermodynamic gradient to drive it. And the fact that we live in a universe where that gradient still exists, where the arrow is still vigorously pointing forward, where entropy is still far from its maximum, where stars are still shining and life is still evolving and consciousness is still arising and asking these questions. This is the most extraordinary fact about our situation that I can think of. We are 13.8 billion years into the universe's existence, and we are still riding the wave of the initial thermodynamic gradient, still surfing the arrow of time, still embedded in the cosmic story of increasing entropy that began at the Big Bang and will end at the heat death, billions upon trillions of years from now. That is a long wave. We are small surfers. But we are real, and we are conscious, and we are asking questions that the universe, through us, is asking of itself. Let us now explore one final territory before we close. The question of what experiments or observations might, in the future, reveal something genuinely new about the nature of the arrow of time. Because the history of science is a history of questions that seem permanently unanswerable being suddenly, dramatically, experimentally resolved. And there are good reasons to think that some of the deepest questions about time might yield to experiment within our lifetimes. The first and perhaps most exciting experimental frontier is the direct detection of primordial gravitational waves. Gravitational waves produced by cosmic inflation in the first tiny fraction of a second after the Big Bang. These waves would be imprinted on the cosmic microwave background as a pattern of polarization known as B-mode polarization. Several experiments are currently underway or planned to detect this signal, including the Simons Observatory in Chile, the CMB-S4 experiment, and the BICEP array at the South Pole. If these experiments succeed in detecting primordial gravitational waves, it would be the first direct probe of the physics of inflation, and it would provide crucial information about the thermodynamic conditions of the universe in its first moments. This is, in a very direct sense, an experimental probe of the origin of the arrow of time. The second experimental frontier is the study of T-violation, violation of time reversal symmetry, in particle physics. We know that the laws of physics are not perfectly time-symmetric at the fundamental level. The weak nuclear force violates a symmetry known as CP symmetry, charge conjugation combined with parity reflection, as was first discovered experimentally in 1964 by James Cronin and Val Fitch, who won the Nobel Prize in Physics for this discovery. By a mathematical theorem known as the CPT theorem, CP violation implies T violation, genuine time reversal asymmetry at the level of fundamental particles. The magnitude of known CP violation is, however, far too small to account for the observed matter-antimatter asymmetry of the universe. The fact that the universe is made of matter rather than equal parts matter and antimatter. This suggests that there is additional CP violation beyond what is currently known, and the search for this additional violation is one of the major goals of contemporary particle physics. The LHCb experiment at CERN and future experiments at planned high-energy colliders are specifically designed to search for these additional sources of CP and T violation. The third experimental frontier is quantum gravity. We do not currently have a working theory of quantum gravity, and the questions that such a theory would answer, including the deepest questions about the nature of time, are currently beyond our theoretical and experimental reach. But the situation is changing. The detection of gravitational waves by the LIGO and Virgo observatories, first announced in 2016 and resulting in the Nobel Prize in Physics for Kip Thorne, Barry Barish, and Rainer Weiss in 2017, has opened a new observational window on the universe, allowing us to probe the behavior of spacetime in regimes of extreme curvature and dynamism. Future gravitational wave observatories, including the planned space-based LISA mission, will probe the spacetime geometry of the early universe, of black hole mergers, and of other extreme events that may yield clues about the nature of time at the most fundamental level. And the fourth frontier, perhaps the most speculative but also the most exciting, is quantum computing. As quantum computers become more powerful and more capable, they will allow us to explore the time-symmetric properties of quantum mechanics in increasingly complex systems. The ability to run quantum algorithms forward and backward, to deliberately exploit the time reversal symmetry of quantum mechanics for computational purposes, to realize and study Boltzmann fluctuations in controlled quantum environments. All of this is becoming increasingly feasible as the technology advances.